For every new price that pops up on the screen, the trader is set in a new state in which he has the option to buy, sell, or hold his position. The aim of this project is to create and implement a trading rule on the S&P index using DQ learning. DQ learning implements deep neural networks to estimate the right action to take and outputs a trade recommendation for every new input it receives. In order to process the data and implement the trading rule, it is necessary to learn to work with environments in Jupyter Notebook. Our environment contains Python 3.6, TensorFlow 1.13, Keras 2.24. Reinforcement learning is an area of machine learning aimed at creating agents capable of taking actions in an environment in a way that maximizes rewards over time. There are many differences in reinforcement learning and between reinforcement learning and regular supervised and unsupervised learning. Amongst the most relevant, we find that in reinforcement learning, we do not tell the agent what to do, how to perform the task, but we do tell it when it is making progress or when it is failing. Besides, the agent needs to find the right balance between exploring the environment, looking for new ways of getting rewards, and exploiting the sources of rewards it already knows. A complete reinforcement learning system is made up of the following elements: an agent, which is a program or machine interacting with the environment which is what the agent interacts with. Models mimic the environment the agent is in it and thus allow the agent to make inferences about its future behavior. States, which is the condition of the environment and the position of the agent in it. The action, which is an activity the agent performs in an environment. It should be noted that agents choose among a list of possible actions. Then we have the rewards, which is the result of action A in state S. Rewards could be positive or negative. The agent's sole purpose is to maximize the cumulative or total rewards. Based on the reward signal, agents can draw conclusions as to which actions are good or bad. Rewards accumulate over time and sum into a final total reward. The policy, which is a function or algorithm or rule specifying how the agent picks actions given a certain state of the environment. Then we have the discount factor, which is a multiplier for future rewards as perceived by the agent. It is a measure of how much the future is valued relative to the present. And then we have the value function, which is a prediction of future rewards used to evaluate the goodness or badness of states, and therefore it allows the agent to select the best amount between actions, best action. The three of the most important formalists of reinforcement learning are policy gradients, Markov decision process, and DQ networks. Markov decision process are based on Markov chains, which were conceived by a Russian mathematician called Andrei Markov. At each step, an agent can choose one of several possible actions, and the transition probabilities depend on the chosen action. Some state transitions return some reward, and the agent's goal is to find a policy that will maximize rewards over time. Bellman found a way to estimate the optimal state policy of any state S, which is the sum of all discounted future rewards the agent can expect on average after it reaches a state S, assuming, which is something very important, it acts optimally. Value iteration estimates are guaranteed to converge to the optimal state values corresponding to the optimal policy. Knowing the optimal state values can be useful in particular to evaluate a policy, but does not tell the agent actually what to do. Bellman found an algorithm to estimate the optimal state values called Q values. Once again, you start by initializing all the Q values to 0, and then you update them using the Q value iteration algorithm. Q-learning is a model-free reinforcement method. This means that it does not require nor use a model of the environment to obtain an optimal policy. For each state S, the algorithm simply keeps track of a running average of the immediate rewards the agent gets upon leaving that state, plus the rewards it expects to get later, assuming it acts optimally. Similarly, the Q-learning algorithm is an adaptation of the Q-value iteration algorithm to the situation where the transition probabilities and the rewards are initially unknown. Q-learning algorithm is represented by the following recurrence equation. Q-learning can work only if the exploration policy explores the Markov decision process thoroughly enough. A purely random policy is guaranteed to visit every state and every position many times. However, it may take extremely long to do so. Therefore, a better option is to use an epsilon greedy policy. At each step, it acts randomly with a probability epsilon, or greedily, choosing the action with the highest Q value with probability 1 minus epsilon. The main problem with Q-learning is that it does not scale too large. However, using deep neural networks can make it work much better, and it does not require any feature engineering. A deep neural network is used to estimate the Q value. A deep neural network used to estimate Q values is called a deep Q network, and using a deep Q network for approximate Q learning is called deep Q learning. Having understood how deep Q learning works, we can now pass on to describing the model we worked with. The model pictures an agent being noticed about the new state that contains the past 10 price observations. Based on this, it can either act randomly or follow what the Q values indicate by the function called def_act. Once a trade that is buy, sell, or hold is performed, the algorithm sees the reward and then accumulates this data together in the agent memory list, together with the action taken, the state, and the future state. Once reach this stage, the Q values are recalculated, and the deep neural network is retrained using the information contained in the memory and the new Q values as labels. This model is trained until there is no more data left and has repeated its process for 300 runs. That's the number we chose in this case. But you can choose the one you want. In order to have a better understanding of how the model works, we thought it would be useful to describe a discrete version showing how the Q values are updated. That is, for a given state, the agent looks at its current Q value, Q table, and performs the action corresponding to the highest Q value. Afterwards, the environment replies by showing a reward and the new state. The model passes now on to updating the Q value by calculating the Q value associated to the initial state. This stands for replacing the former Q value for a tuple state, for the tuple state action SA with a new one. In the case of applying deep neural networks, we pass on to actually updating the weights of the model that will be used to estimate the Q values the following time. Now having said all this is the output we get for every new output the model receives and in the chart describes the average moving average of the rewards obtained in all every time the whole model was run, which is 300 in total.